I'm Mark, now the CTO at Logicstar, and in my prior life in academia, if you will, I worked on provably robust machine learning systems at ETH. And today, indeed, I'll talk about code agents in the real world. And let me begin by outlining the promise that various companies in the space make. Cursor, for example, who just recently had big news to share, raising 2.3 billion US dollars, not as evaluation, but actually as money raised, promised that their code agents will make any developer that uses them orders of magnitude, multiple orders of magnitude, so 100x or more effective. The CEO of Anthropic, Dario, said in March that in 6 months' time, so already now 90% of all code will be written by AI. So with these promises being made, let's have a small look at the reality. But before that, we talk a lot about agentic AI. Let us briefly outline what that actually means. And to motivate this, let us look at what we really want to do with AI. In academia, I try to solve interesting problems. Now in industry, I try to solve valuable problems because people are a bit more willing to pay for that. And in the space of software engineering, kind of maybe the value hierarchy is something like auto-completing a single word is very low value, but can happen very quickly. Then implementing a simple function provides a bit more value. Fixing and investigating bugs is more valuable yet. And implementing complete features perfectly is obviously very valuable. Unfortunately, solving these complex, valuable problems turns out to be hard. And what does hard mean here? Both humans take a lot of time to do it, and ML systems have low success rates at doing this. And LLMs are not that amazing yet. They often fail even on relatively simple tasks. If you give this task of counting how many R's are there in the word strawberry, now all frontier models will solve this without issues, but if you give it even to recent generations, slightly smaller, cheaper models, they will actually still fail at this. And if you compound many such moderately complex or even very simple tasks that your LLM needs to handle correctly, then chances are that it will make errors at some point. And if these errors are not corrected, we will end up with a failure in almost all cases. So how can we make LLMs successfully solve more tasks is the question that ultimately led to agentic AI. And when we started using LLMs, we started with a very simple workflow. There was a prompt, in a way a task that we gave to an LLM, and it provided immediately a final response. And you can think of this as your immediate gut feeling, a gut answer that you give out of an instinct. And if I would ask you to solve any of these more complex tasks just like this without any iteration, most of you would probably also fail. So what the community developed is essentially agentic systems. Here you give the original prompt, the original task, to the model, and then it can interact with an environment. And this environment may be the web at large, or your code base, or some set of tools, and then it can make changes in this environment, for example, by writing tests, modifying code, making search requests against the internet, making queries in some database, writing an email, and it will be returned some observation from this environment. And given some task, now we can iterate on this until the LLM believes it has completed this task, or there's some framework around it that will say, enough is enough, you've tried 100 times to do this and failed repeatedly, so we'll stop this now. And what is interesting here is now the result is not only the final response of the model, but also all changes in the environment. And so what agentic AI really is, to me at least, is it's essentially some sort of ML model that has a state and the ability to observe and interact with an environment over multiple turns. And this is quite powerful. For example, in software engineering, there's lots of companies offering different slices of products here, including ours, but often it boils down to a sequence that's roughly, you give the model or the agent a task, it will come up with some sort of plan, then it will begin editing and writing tests, and in the end, if you're lucky, it validates its solution. And depending on what solution you go with, there will be a different focus on different aspects. Maybe some will be enforced. For example, we put a lot of effort in enforcing the testing and validation stage such that agents cannot just decide they know they're good and thus they skip it. And others put a lot more focus on, for example, the planning stage. So with this being said, how can we now benchmark how good these agents and models are? Because as we said before, you can't optimize what you can't benchmark and you can't trust what you cannot observe. So this is really crucial both for developing and also for using these tools. And what evolved to be, at least initially, the gold standard for determining the performance of code agents is SWE-Bench, or Software Engineering Bench. And here the task is quite simple and yet reasonably realistic. You take real GitHub issues and the corresponding states of the repositories, and then you task an agent to fix these issues. And then you also have an original pull request that some human wrote back in the day, including some tests. And then you compare the pull request that your agentic system created with this human written one by executing the human written tests. So we have some tests which allow us to evaluate the correctness of the change, and the code base in general is hopefully well tested, so we can ensure that we don't break any other functionality. And the genius, if you will, or at least what makes this work well compared to methods that existed before, is that in code there's a lot of solutions that are correct, and really functional correctness you can best measure by having test cases. And sourcing realistic test cases for realistic problems at scale is difficult, so using real GitHub issues is a great approach. And when this was originally proposed, about 2 years ago, performance on this benchmark was incredibly poor. The best models at the time achieved 2% if they were not trained specifically on this task, even with a dedicated harness, and about 10% if they were trained specifically on this task. And over the 2 years since then, performance has really skyrocketed, up to around 80% now, where there's a lot of discussion on whether the remaining tasks are even solvable generally, or if you basically need knowledge of the ground truth solution, for example, because you need to output a specific string to pass some test that you cannot really guess. So this raises the question, of course, a little bit naively, is software engineering solved? If on this supposedly very realistic benchmark, we achieve already 80% accuracy. And this, of course, immediately leads to the question, how representative is this benchmark of real-world use, right? And what we see is actually, first of all, it's only Python, which is only a small slice of reality, but then there's only 12 libraries. And actually 50% of the benchmark is just 2 libraries. And all of those instances that we look at are actually older than the most recent data that the models were trained on. So if some model provider was not very careful in the best case, or maybe even nefarious in the worst case, they might have included this data in the training, and thus can inflate their performance. So to answer this question, we automated the benchmark generation, which essentially boils down to scraping thousands of GitHub repositories, scanning them for suitable pull requests with tests, and then automatically setting up the execution environments, which actually turns out to be the hardest part, because everything else I can basically get directly from GitHub and just evaluate with simple heuristics, but setting up the full execution environment to actually run the code efficiently turns out to be a little bit harder. So we developed this somewhat complicated system to do this. We did this about 1.5 years ago. Nowadays, agents are probably much better and don't need so much help in doing this, so I'll not bore you with the details. But what we basically find is here we generated these two, the blue and the green curve are basically our new benchmarks, and here the orange curve is the original benchmark. And our new benchmarks here have a lot more focus on recency, on recent issues, looking at various characteristics of issue descriptions, and basically if the curve here is further up and to the left, that means that there's more instances that have a lower value of whatever we have here in the bottom. Issue descriptions are roughly distributed similarly, and a small spoiler, this does not hold at all once you leave open source. If you look at actual company problems, you'll get a completely different distribution of how people describe their issues, which actually turns out to be a big challenge, but unfortunately I can't show you this data from customers. But also what we see is that this original benchmark is not very representative when it comes to the hardness of the fixes. They tend to be smaller, affect less tests, include fewer lines. So generally we see it's not a very representative benchmark. And if we now look at what is the effect of this on the actual performance of these agents, and thus what we can expect in real-world use, is we actually see, if we go from this original benchmark that I showed you, the 80% performance early on, to not filter specifically for well-specified instances, and then not sample only popular repositories that the models will probably have been trained on, and then further only look at issues that were actually created after the model's so-called knowledge cutoff, so the end of their data collection, then we see a dramatic decrease in performance. So these are not the numbers that we crunched when we wrote the paper. For newer models and newer agents, this is not as dramatic, but the trends remain the same. So what is here perhaps the takeaway is, when you read these benchmarks results, you have to be very careful if they're really representative of your use case. Just because some agentic system or some model achieves 80–90% performance on an academic benchmark that sounds similar to what you're doing doesn't mean at all that you will actually see this performance. And it's crucial that you test and benchmark specifically on the use cases that you want to deploy these models on. So much for benchmarks. What have we observed as real-world impact? And one thing that we can say for sure is that these systems have been commercially extremely successful. Cursor and Lovable, for example, have been two of the companies that reach 100 million and 1 billion in the case of Cursor ARR, the quickest of all. And if you look at the prevalence of code agent use, at least on open source code, we see that's extremely prevalent. And what we did to analyze this is we scraped every single pull request that was made on GitHub over the last 6 months, which is roughly 30 million of them. And we looked for indicators that they were created primarily with code agents, listing here a bunch of the more popular ones, the most popular being Codex with almost 2 million pull requests. And we see that about half a year ago when these systems were introduced, we begin to see quite consistent usage here of Codex, and then the end, I'll show this a bit larger, there's some change, but we don't really see any decline in human pull requests. In fact, we here even see some increases in human pull requests, and this oscillation is simply on the weekend people code a lot less. So we see there is good adoption, not replacement so far. And if you look and compare the different code agents, we see Codex dominates, at least on open source issues. And then recently, here, the Claude Code agent has jumped in popularity and overtaken Codex with somewhat a surprise contender. Sadly, you can't see the color so well here. But this is actually Google Jules, which many of you may not have heard of, but it's actually reasonably popular and successful. But this just shows you a lot of people are playing with this and a lot of people are using it, but how good are these pull requests? And one way to answer this is to look at the merge rate. This is hopefully, at least for big repositories, so we look here at the number of stars. There's a reasonable review process in place and bad pull requests are rejected. So this should give you a decent indication of how good the pull requests are. And here basically at the top, this line is human pull requests, and what you can see is the best agents are roughly on line with merge rate, with human pull requests in the same projects. One thing to keep in mind, all of these here have some human interaction with the pull request before, and humans only open the pull request if they're generally happy. But this shows that with heavily assisted pull requests, you can achieve roughly similar approval by your peers, at least. If this is now a very short-term measurement of quality, just does it pass a human review? And if you're using code agents regularly, you will know that they often produce very large pull requests. And if they produce a 1,000-line pull request and now you ask some unpaid open source developer to review it for you, they will probably either decline it or they more just glimpse over it and not actually carefully read every line. So to measure more properly what the impact is, you need to take a more long-term view. And what you there observe over time, that indeed we develop tasks or we complete tasks faster with code agents, but there are some quality trade-offs. PRs do take longer. There's a lot more churn, which means the same code gets touched again after a short time, here I think 2 weeks. There's a 9-fold increase here in this study in duplicate code, and I'll discuss in a bit why that is, or a hypothesis of why that is. And there's more bugs and more static analysis warnings. And now there was a recent CMU study actually looking at the causal effect of, in this case, introducing cursor. And what they found is that the number of commits and the number of lines added jump heavily in the first 2 months after cursor was adopted in an open source repository. But afterwards, these fall back to baseline levels, and there's kind of no consistent and persistent improvement in productivity. But when they look at indicators of technical depth, namely static analysis warnings and a code complexity metric, you actually see that these jump and stay high. So here, at least in this study, and this data is from spring, so maybe new systems are better, but we see that you get short-term productivity gains for long-term pain. So you have to be mindful when you adopt this. And if we now look at our study of 30 million pull requests again and compare human versus agentic pull requests, we see also indications of this. Here, this is the ratio of added versus removed lines. So simply modifying a line will sit here at 50%, and simply only adding new lines is here at 1.0. And we see that the ratio of pull requests where we only add lines is almost twice as high for agents. So they just tend to add a lot more code, which makes it less maintainable generally. And the question is why? And one very obvious answer is the problem of context. If you have ever been onboarded or onboarded yourself on a new code base, you know that this is reasonably hard. You first have to learn what's the architecture, where does everything live. And for an agent, this is no different. It basically has too little context to see the whole code base at the same time, and has to go and explore the code base using these actions, tools like, for example, grab or find that I mentioned earlier. And it does this step by step, collecting one document after another. And if it now wants to, for example, find some utility function that was not perfectly named and the architecture is a little bit messy, it's actually quite difficult to find this. And it's really super easy for an agent to simply spit out 100 lines of new code that hopefully does kind of the same, which is horrible for the maintainability of the repo, but makes the task of the agents a lot easier. And the bigger problem is you as a human might be tempted to do the same, but first of all, writing this 100-line function is a lot harder for you and will take a lot more time. And you know that if you go and dig for these utility functions, you will be able to use them for the next months and years that you work on this project. Unfortunately, for now at least, for agents, every code base is new every single time that they try to solve a problem, because they don't have a persistent memory. We try to give them something like this with cursor.md or agent.md files, but it's not really a memory, it's like a README that they read every time. And here, kind of an open challenge is, how can we make these systems really truly learn continuously? And it's also something that we work on. And one answer or one approach that we pursue is to provide a knowledge graph to the agent that encodes a lot of this information to make it a lot easier to find the information. So how is it really to work with these agents and what really matters there? And if you look at what really drives efficiency gains, you see that the time that the human has to spend per PR that's created by an agent is actually less dominated by the success rate of the agent, although this is important. But once you reach a reasonable level, it actually becomes dominated by the time required for the review overhead. So what is really critical is to design systems that are efficiently reviewable. And now the time is running a bit short, so I'll go a little bit high level, but basically doing a full manual review is horrible. It just pushes the bottleneck to the review. So what you want is a sort of self-validation and self-review, that the agents have a lot of filters built in to write tests, validate the correctness of what they do, and then present basically a proof to the human, such that the human only has to check, is basically the goal of my proof, my theorem, correct, instead of looking at the actual full proof. And in the case of coding agents, this is basically tests. The agent has to write good tests that efficiently cover the desired behavior and then show you that indeed these tests now all pass. And you can just check the code of the test, and if you're convinced that the test cases cover the intended design on your side, then you know that the implementation is correct. I'll skip a little bit on how exactly this works. We developed some benchmark on how to efficiently generate such testing benchmarks. And using this to improve our own agents, we actually see that we get a 6-fold reduction in the review overhead if we fully leverage all the test sets we generate. And we optimize our interface to basically speed up this validation process. But in contrast to a standard code review interface, we put a lot of focus and value on showing you the actual test results before and after a change, so that you can directly compare these things, which gives you a lot more trust in, for example, that the test actually captures the problem that you're interested in, because you see it fail on the original state of the code base, so you're convinced that this test actually reproduces the problem that the agent is trying to solve. So let me leave you with a summary of what I told you today. Agentic AI is really an LLM or other ML systems iteratively interacting with an environment. And implementing such systems kind of at the moment gives you short-term gains, but sometimes long-term pains. And to alleviate this, we need a more efficient review process that puts focus on reducing review overhead while keeping review quality high. And with this, I want to thank you and take some questions if you have them.
Thank you, Mark. Any questions?
Hello, thanks a lot for the very interesting talk. I had 2 questions, but I'll leave one for the coffee break. The question I want to ask here is, so it seemed like a big problem is this continuous learning or understanding the code base in a persistent manner, but connecting to what was presented before, how do you make that secure? Because if I kind of inject some malicious instructions and those are persisted in your memory, then I kind of create a backdoor that will persist over time.
Yeah, that's a great question. So I think there are different usage patterns depending on who basically has access to the input of your agent. So one solution that we are currently working with is analyzing your current code base. So in this setting, only people that actually have right access to your code base can impact the agent inputs. And then we use static analysis to understand the code base. But this is not so relevant for the security aspect. So they're really only people who already can have arbitrary access to your code base and no real incentive can cause harm. And then the next thing is you can put human review layers in place to kind of validate these learnings and kind of repeatedly review them such that single bad instructions are unlikely to persist. But this is very difficult. So it's a great question that as soon as you expose your systems to malicious inputs, which is essentially anyone who doesn't have full privileges already, this becomes a bit hairy.